Last video we calculated all the angles for all the different charges, and now we know the directions that the forces are going to point. So the next thing that we need to calculate is the magnitude of the forces, and the only ones that we really have to deal with are the forces along each side and the forces in the diagonals. Once we have those two, then we can come up with all the different combinations for the next part. So for the force of charge 1 due to charge 2, that's just going to equal our constant k of the charge times the square root of q1 times q2 over the distance r12 squared. And the reason why we're using the absolute values in this equation is because the angles have already been determined from the previous analysis. And so the angles will then give us the positive or negative forces components that we will be looking for based on the sines and cosines, but we only need an absolute value or the positive value for the force. And that's the one difference with the component view than with the vector view. So that's going to be our constant k is, let's look that constant up. I gotta get my notes out here. That constant k is, where is it? Ah, there it is. So we have 9 times 10 to the 9th, and that's newtons meters squared per Coulomb squared, times the absolute value of 4.15 times 10 to the minus 3 coulombs. That's for millicoulombs, 10 to the minus 3. And since it's the same magnitude for both, we'll just put squared here. Divided by our distance is 0.100 meters squared. And that is going to equal 1.549 times 10 to the 7th newtons. So our force 1,2 is going to be equal to force 2,1 is equal to force 2,3 is equal to force 3,2 equal to force, let's see, it should be an F, force 3,4, force 4,3, force 4,1, and force 1,4. That's all of the edge forces there. Now for our force along the diagonals, we have force 2,3 is equal to k of the charge times q2 times q3. We're going to take the absolute value divided by r23 squared. And we have 9 times 10 to the 9th Newton meter squared per Coulomb squared times the absolute value of 4.15 times 10 to the minus third coulombs squared over, now this is the diagonal, so it's going to be the square root of 0.100 meters squared plus 0.100 meters squared, and square that. So the square root's basically going to go away. And we calculate this out, and we get 7.743 times 10 to the sixth newtons. Now I'm just going to show for the force on charge 1. In the notes you have for all of the charges that you can look over, but once you see how it works for charge 1, it's the same process for all the other charges. You just have to keep track of your subscripts. So for our force on charge 1 in the x direction, we're going to have force 1, 2 cosine theta 1, 2 plus force 1, 3 cosine theta 1, 3 plus force 1, 4 cosine theta 1, 4, and that is our total x direction. So we can put our values in here. And we have 1.549 times 10 to the 7th newtons times the cosine, and our theta 1, 2 is 90 degrees. Force 1, 3 is going to be 1 point, or I'm sorry, that's not 1 point, it's the diagonal, so it's 7. 7.743 times 10 to the 6th newtons cosine, and we need angle 1, 3. So angle 1, 3 is 225 degrees. Plus 1.549 times 10 to the 7th newtons, because it's one force between 1 and 4, so it's along the side, cosine, and theta 1, 4 is 0 degrees. And we calculate this out, we get 1.001 times 10 to the 7th newtons. And now we do for the y component, do on force 1, and that's going to be F12. And now, because it's in the y direction, instead of the sine or cosines, we're going to have sines. Right? So just remember, cosines go with x, sines go with y. So you see it's just a copy of the same formula For the x, just change all the cosines to sines. And I'm going to have the 1.549 times 10 to the 7th newtons. I need the sine. And the angle is going to be the same, so that's 90 degrees. I'm going to have the same force, 1,3. Sine is going to be of the same angle, 225. And that'll be this, for the last one, will be the sine of 0 degrees. And now, can calculate that out, and I get 1.001 times 10 to the 7th newtons. So here's my x component and my y component. If I want to find the complete magnitude of the charge, then it's going to be equal to the square root of f1x squared plus f1y squared and I'm just using the Pythagorean theorem for the x component and the y component, and that gives me 1.416 times 10 to the 7th newtons. Oh, went too far. And our angle, theta 1, the angle of the force, well, it's the F1x and F1y are in the both positive, so that's just going to be the arctangent of F1y over F1x and that turns out to be 45 degrees. So this is how we calculate the force on charge 1. Now notice that in the subscripts for the individual forces that I'm looking at from all the other charges, the first subscript is always the subscript of the force that I'm trying to find. So in this case, I have 1 as the first. The second subscript is all of the combination of all the others. So I have 2, 3, 4. But I'm not going to have the same as the first charge. So I'm not going to have force 1, 1. There is no such thing as force 1, 1. So for force 2, you're going to have 2's in the front, first indice, and then you're going to have everything other than 2. So you're going to have force 2, 1, 2, 3, 2, 4. And just keep track of all your angles and the sines and cosines, and you will be able to do this. It's all counting. Now, if you look at the notes, it gives you the forces for all of the charges. And what you notice, which is very interesting, and I'm going to put this in blue. You'll notice that charge 1 is going in the 45-degree direction, and charge 2 is going to be going in the minus 45-degree direction. Charge 3 is going to be in the direction of 225 degrees, and charge 4 is going to be in 135 degrees. They're all pointing towards the center of this square. And it makes sense because even though the opposite charges are the same and would repel, the distance is further away and the green charges, the opposite charges, are closer and they're balanced. So it's going to have a tendency to draw the corners in. And the closer they get, the greater the force, but it's always going to be with the vectors in the same direction pointing towards the center. So we can interpret the results of the problem, and they should make sense with what we see in this. In this case, the symmetry tells us that we're correct.